This work was done in collaboration with my research mate, Professor David Taylor. We did this work in Ireland last year, and actually we invaded a field which is not our usual field because my background is in fatigue, but we tried to extend the classical idea also to the multi-axial, to the static assessment of ductile materials subjected to multi-axial loading. So basically the aim of the work is to see if we can predict static failures in ductile materials by forcing the material itself to obey a linear elastic law. In other words, in these situations, fatigue damage is preceded by large-scale plastic deformation. This final breakage is preceded by large-scale plastic deformation, so the obvious choice would be modeling the plastic behavior of the material, but engineers don't like it so much, so they love when we can say, okay, you can do everything by doing a simple linear elastic model. So let's start from the experiment, because before formalizing a static assessment procedure we had to understand something about the material cracking behavior under multi-axial loading, and basically we tested the samples of a conventional aluminium 6082, and the UTS of this material was 367 megapascal. We tested samples, cylindrical samples under combined tension and torsion, and basically we tested V-notch specimens, and the net diameter was equal to 6 millimeters, and the notch root radius ranged in the interval 0.44 millimeters, 4 millimeters, resulting in an axial KT value in the interval 2.94, 1.33, and the torsional KT in the interval 1.71 and 1.12. So a variety of notches, considering also a variety of ratios between the two nominal components, stress components. Well, as you can see from this first slide, this is a conventional stress-strain curve plotted in engineering quantities, and according to the observed fracture surface, the investigated materials show the conventional ductile behavior, a classical cup and cone failure. And here you can see under simple tension the results obtained by testing the specimens containing different geometrical features. And of course this is the plane curve, as you can see the other curves are above the reference one, and this is the classical strengthening effect, that is the plastic zone is surrounded by a bulk material which behaves elastically, and the overall result is in an apparent increment of the strength of the material when plotted in terms of load versus extension curves. Well, the cracking behavior under simple tension was quite conventional when dealing, of course, with notches, and basically, as to the bluntest geometry, you can see that the maximum point in the curve corresponded to the onset of necking, and the final failure was characterized by a cup and cone surface, so we have no stable propagation before final breakage takes place. But on the contrary, when moving to the sharpest geometry, it's interesting to see that the maximum stress recorded in the load versus extension curve corresponding to the initiation of a stable crack, a ring stable crack, which was followed by a fast fracture, mode 1 fast fracture, resulting in a quite rough surface. Under simple torsion, these are the conventional curve, torque versus twist angle curves, and in this case we had no strengthening effect, and the cracking behavior was rather complex. That is, the maximum in the recorded curve corresponding to the initiation of a stable crack, which kept propagating as the applied torque increased, resulting in this particular surface, cracking surface with circular and concentric marks. And this is the case for the bluntest geometry. So basically we had no evident plastic deformation according to the involved damaging mechanisms. And a similar behavior was observed also testing the sharpest geometry. The notch root radius in this case was equal to 0.5. Again, the UTS was assumed to be the maximum in the torque versus twist angle curve, and again the maximum point corresponded to the initiation of a ring crack, which propagate in a stable manner before final breakage occurred. So far, no problem. We use the classical definitions to define the UTS, both under tension and under torsion, that is, the maximum loading recorded during any test. But when moving to combined tension and torsion, the situation became much more complex. For instance, this is the curve generated by testing specimens having a notch root radius equal to 4 millimeters, and the ratio between the two nominal stress components was equal to 0.23. And as you can see, the maximum, the UTS of the uniaxial curve is not aligned to the UTS of the torsional curve. And the problem is that since we had to keep this ratio constant during test, of course we had to, the axial strain rate was different to the torsional strain rate, resulting in this particular situation. But it's a matter of scale, basically. We could rescale the diagram to align the two points. But I think that the situation becomes very clear from this diagram, which plots the applied loading against time. And as you can see, the ratio between, at any instant, the ratio between the two applied loading, the two applied stress components is constant. And as soon as the maximum is reached in the torsional curve, basically the behavior of the material becomes absolutely unstable. So we can assume that that point is the UTS under torsion, under combined loading. So, and in any test, independently of the ratio between the two nominal loadings and independently of the sharpness of the notch, we got a situation like this one. That is, the maximum was always reached sooner in the torsional curve than in the uniaxial curve. And the cracking behavior was quite complex, because for the bluntest geometry, and for instance, assuming taking this ratio between the two nominal stress components equal to 1, we had no crack, and basically the maximum corresponded to the initiation of a conventional ductile fracture. We have a lip here at 45 degrees to the specimen axis, and an horizontal and a crack, a propagation perpendicular to the specimen axis, which was characterized by a fast fracture behavior. When moving to the sharpest geometry, the situation is completely different, because the maximum in the torsional, in the uniaxial curve, corresponded to the initiation of an unstable crack. So the surface was characterized, the final fracture was characterized by an initial stable propagation, a ring stable crack, and an internal fast fracture surface. Well, so as you can see, this is the matrix summarizing the obtained results. We have a kind of ductile behavior in this area. Actually, sorry, this matrix plots reports the ratio between the applied nominal loadings and the sharpness of the notch in terms of notch root radius. So basically we moved from an area characterized by a kind of ductile behavior to an area where the final breakage was characterized by the formation of ring stable cracks, to conventional fast fracture that is a kind of brittle behavior. And these are the results in terms of UTS under biaxial loading. Of course, we tested for any geometry and loading configuration. We tested from 3 to 4 samples, and this represent the average values obtained. So we tested in the end more than 150 samples to generate this matrix. So now the problem is predict these failures using a simple linear elastic model. So we went back to the classical theory of critical distances, which can be summarized this way. Basically, we have two material properties, L, which is a critical distance, and sigma naught, which is the inherent material strength. So, a failure is supposed to occur when the stress, calculated using one of the conventional hypotheses like Mises, Tresca, or the maximum principal stress, reaches a certain critical value, which is in fact equal to the inherent material strength. Or, if you want to apply the theory of critical distances in terms of the line method, the sigma, the effective stress has to be calculated by averaging the equivalent stress, the adopted equivalent stress, over a line having length equal to 2 times L. So this is the idea, and don't forget that these stress fields are obtained by assuming a linear elastic behavior of the components, so that those stress fields have to be plotted in incipient failure condition. Well, as you can see, to predict everything we need two parameters, L and sigma naught. So using the point method argument, we can say, okay, we run two tests considering two different notches. We can plot the corresponding stress fields according to the adopted equivalent stress, and the intersection point here allows us to calculate both L and sigma naught. So we need two experimental tests ran under uniaxial loading to calibrate the constants to calculate the material properties. Now, the idea, obviously, is to extend this approach to multi-axial situation, and by checking the validity of this approach through the generated results. So, in order to do that, we explored three different hypotheses. These are the stress fields plotted in terms of Mises stress, obtained by testing three specimens having notch root radius equal to 4 millimeters, and 3 samples having notch root radius equal to 0.44 millimeters. And from these two curves, using the intersection point, we got the two material properties we need. But the same reasoning can be applied also by addressing the problem in terms of Tresca's equivalent stress, or by using the maximum principal stress criterion. Always the same experimental results to calibrate the constants, but using different hypotheses to calculate the equivalent stress. And in this table you can see that the obtained results, so L is equal to about 0.5 millimeters when using either Mises or Tresca. On the contrary, it is much larger when applying the approach in terms of the maximum principal stress criterion. Okay, but if you have a look here at the inherent material strength, as you can see, it's much higher than the UTS. This is simply due to the fact that we do believe that a cracked material is not an uncracked material, so that basically when we consider a plain material, defects play a fundamental role, lowering the UTS. But when we have either a sharp notch or a blunt notch, the geometrical feature prevails over the damaging effect of the local defects. So the strength, what we calculate here, is nothing but a kind of defect-free material strength. So this is the reason why it's higher. Well, this is the obtained accuracy in terms of percentage error. So we explored, as we say, the different geometrical features, different ratios between the nominal components. And basically, this is the accuracy when the problem is addressed in terms of Mises equivalent stress, and the highest accuracy level is obtained when applying the idea in terms of the point method. Of course, good results are also obtained when addressing the problem in terms of Tresca's equivalent stress, and in this case the line method gives the best results. And you shouldn't be surprised, very bad predictions are obtained when applying the approach in terms of the maximum principal stress criterion, simply because we didn't, and simply because we never observed cracks propagating along the plane experiencing the maximum principal stress. It was a conventional ductile behavior. So let me conclude simply saying that the idea is very promising, but of course we tested the idea using one single material, so more work needs to be done in order to check the validity of the idea itself. But if it works, it is really good, because we can predict static strength of having very complex geometries without the need for defining nominal quantities like a nominal stress, or without the need for running very complex and time-consuming elastoplastic analysis. Thank you very much.